Welcome to our new unit, Simple Machines. This is going to be a little bit of a mini unit that I'm adding on as part of the Dynamics unit because a lot of the topics in here ties really nicely to forces and stuff like that. I'll be honest, I've never taught this as a part of this course before, so this is a new experience. And really the reason why I'm doing it is because a lot of this stuff is really important in your everyday life. And the math isn't too hard, and there's some really cool aspects that you can apply in your everyday life. So we're just going to look at kind of not all the simple machines, but we're going to look at first, what is mechanical advantage? How do we use machines to help us and to our advantage? And what does efficiency mean when it comes to a machine? Then we're going to look at four different types of simple machines: inclined planes, levers, wheels, and pulleys. That's it. There are more than that. There's a couple more I'm not really talking about. We have the wedge and we have the screw. But fun little fact, a wedge is just two inclined planes side by side. So it's actually kind of the same thing. And a screw is also just an inclined plane, but it's just wrapped in a circle. So those we're not really going to talk about. You can look them up on your own time once we've gone through this. I want to focus on the main thing: inclined planes, levers, wheels, and pulleys. Um, they're going to be fantastic. Okay, so before we start, let's look at mechanical advantage and what that means. Mechanical advantage is a ratio of how good the machine is, essentially. It compares the output force to the input force, or what we like to call the effort force. So what is the output force? So essentially this output force is the force needed. Okay, and when I say needed, I mean needed to complete a task. So if we want to lift something, then based on what the weight is of that object, we need a specific amount of force to be the output force. The effort force or the input force, this is what we are putting in. This is what you put into the machine to get out the output force. And the mechanical advantage is this ratio that multiplies the amount of force that you put in. Now, because it's a ratio, it's unitless, which is really nice because you can work in whatever units you want as long as you are consistent. So the formula for mechanical advantage, which we like to use as this MA, and we got a couple different definitions. I'm lazy to write mechanical advantage out all the time, so I'm just going to use MA. So this formula, it's just a ratio of your output force divided by your input force, which if you like variables and stuff, you can call this F naught or F zero or F out and F in. So usually these things are used to move or lift an object. So like I was just talking about, that output force is sometimes going to be what we call the weight of the object, right? Since if we are trying to lift an object up, then we are fighting against the weight of the object. That's the amount of force needed as an output. We don't want to put all of that force into the machine, right? We want the machine to help us out a little bit so we don't have to work as hard. That's what simple machines do. So very simple, quick examples about this. If a machine takes an input force of 15 newtons and creates an output force of 60 newtons, what's the mechanical advantage? So according to our formula, right, the mechanical advantage is going to be output divided by the input. So if we are putting out 16 newtons of force and we are inputting only 15 newtons, making sure our units are exactly the same, this gives us a ratio of 4, okay? And that right there is our mechanical advantage. It is 4. This machine is increasing our effort by a factor of 4. So if we were put in, say, 25 newtons, we would be able to lift up something that is actually 100 newtons in weight, okay? And so on. So that's really cool. Your mechanical advantage is pretty much always, like 99% of the time, is going to be more than one, right? We don't want a machine that makes work harder. That just doesn't make any sense. We want these machines to make our lives easier. So another example of this, we've got an object with a mass of 428 kilograms hooked up to a pulley system. When it's done, the user only has to pull with 1400 newtons. okay? But if we do a quick, even before we finish reading the question, if we look at the weight of the object, this force of gravity, which is mg, this 428 kilogram object, 9.81, then that means that this force of gravity is going to give us 4,198.7 newtons, right? That's how much force we need to lift this thing up, right? So that right there has to be our output force, okay? That is what we need as an output. But the question is telling us that we only have to input 1,400 newtons in order to accomplish that, which means the mechanical advantage of this system, which again is going to be the output divided by the input. Well, if we are outputting 4,198.7 newtons because that's what we're lifting, but we're only doing it by inputting 1,400 newtons, then that tells us that our mechanical advantage is 3. So this machine is tripling our input force, which is pretty good, pretty helpful for just some pulleys. Okay, so that is mechanical advantage. Now, a lot of times in life, we're dealing with distances, right? We're going to have to move things a distance. That's the whole point of this. We're moving objects, but nothing is free. These simple machines sacrifice one property to make gains in another area. It's like anything in your life. If you compromise, say, I don't know, a job that you really, really like but doesn't pay as much compared to a job that you hate but pays really well, that's a compromise, right? You can't have both. I mean, some people can, but they're pretty lucky. Um, Simple machines are exactly the same thing. So the last example we did has a that machine had a mechanical advantage of 3, which means we can lift objects with 3 times less force. But the trade-off is that we have to actually pull 3 times further at that lower force. Okay, so if you might only want to lift, let's say you want to lift that mass up 1 meter, well, we don't have to pull 1 meter at 1,400 newtons. We have to pull 3 meters at that 1,400 newtons in order to accomplish the same distance traveled. So, right, nothing is free. It's just a trade-off. It's not the end of the world, because if we are really decreasing the force to a really manageable way, then we could push that thing for a lot longer and we're not going to get tired because we're not straining ourselves. So we can compare our mechanical advantage in terms of distances as well. And so really we say our effort distance divided by our output distance. And you can put DE and DO if you want, but it really doesn't matter. All we're saying is, right, this effort is saying how far do we have to pull? And then our output is saying, what do we need? Right? What do we need? Like in the last example, let's say we need 1 meter of distance moved with a mechanical advantage of 3. That means we need to pull it 3. Our effort has to be 3 meters. Okay? But everything else is exactly the same. We're going to talk quickly now about efficiency, because friction exists, right? We know that friction, a lot of times in physics, we assume that we live in a frictionless world, but that's just not true. So when we talk about mechanical advantage, we talk about an ideal system where there's no friction. What we do is we call this the ideal mechanical advantage, or IMA. If we put in 5 newtons of force, we expect all of that energy, that force, to be transformed into something bigger. In reality, obviously, that's not how it works. We lose some of the friction, heat, and anything else. So what we do is we call that the actual mechanical advantage, or AMA. Now, questions will specify exactly if you're dealing with AMAs. If it doesn't say, assume an ideal system. Okay, but if it tells you anything about efficiency, you know you're dealing with an actual actual mechanical advantage, or an MAA. Okay, and it's super important to note, because we're dealing with actual stuff compared to ideal stuff, the AMA will always be less than the IMA. So the actual, what we get out, will always be equal or less than the ideal mechanical advantage, because nothing in life is free, right? Just like we talked about with inclined planes, friction never pushed anything up a ramp, right? Friction always holds things back. In order to calculate the efficiency of a system, it's expressed as a percentage as a ratio of the two mechanical advantages. So our actual divided by our ideal, okay, multiplied by 100%, right? This is a percentage. It is the ratio of how good your system is compared to what you want it to be, what you expect it to be, okay? You can also find efficiency with forces, with essentially what you're looking at is your input force divided by your output force, where, right, this is what you expect to put in, and this is what you actually have to put in. So we can add put in, expect to put in. I don't love doing it this way. It's possible. I like comparing the mechanical advantages because it just makes more sense that way. But again, it's just ratios, so you can do whatever you'd like. So let's do a bunch of examples with this stuff, talking about effort distances and stuff and efficiencies. So we want to move some boxes into the back of a truck, 1.5 meters off the ground. You built a ramp that's 6 meters long. What is the mechanical advantage of this ramp? So what we just learned, right, our mechanical advantage is going to be our effort distance divided by our output distance, okay? Our effort, we are going to push for 6 meters, right? That's how long we push for. And where we are going with this is 1.5 meters off the ground, right? That is our end result. Both our units are the same, meters and meters. I could change them to feet and feet, yards and yards, football fields and football fields. It doesn't matter as long as it's the same unit, because 6 divided by 1.4, whatever the unit is, we are going to get a mechanical advantage of 4. So that means if you are lifting something that is 100 newtons, you only actually have to push that object with 25 newtons, and we will go up the ramp. Yes, you have to do it 4 times as long, right? 6 meters is 4 times longer than the height you were trying to get to, but you did it with a lot less force. Cool. Question number 2. This one is yours. You can have that one. Again, it's just a ratio. Go ahead, have fun. It's exactly the same idea. Okay. Question 3, let's do it. We're dealing with a pulley system with a mechanical advantage of 3. We wish to lift a 20 kilogram object up 15 meters to the roof. We want to know how much force do we have to pull with. Okay. So how much force? If we were lifting straight up, okay, I don't know why I'm using this box right now. Okay, if we want to lift straight up, we would have to fight fully against the force of gravity, which is mg, right? Which means the force of gravity, 20 times 9.81 is going to give us a nice, beautiful 20 times 9.81 is going to give us 196.2 newtons. That is how much effort we'd have to put in. But we have a pulley system, right? That has a mechanical advantage of 3, which means we're not going to have to put in all that force. We have to put in a factor of 3 less. So our mechanical advantage, which again is output divided by input, we know it's going to equal to 3. We know it has to output 196.2 newtons. We want to know how much force do we have to put into this thing, which means we just multiply by input, divide by 3. Well, the input force is going to be 196.2 newtons, again, keeping the units consistent, divided by our mechanical advantage of 3, which means our input force, 196 divided by 3, we only actually have to push or pull for 65.4 newtons. So we've decreased the amount of force by a factor of 3. That's all fantastic, but now we want to know how far do we have to pull the rope to lift it, right? If we are fighting against full gravity, if we have no system to help us, no system to help, then we have to pull 15 meters. We're pulling a super heavy weight of 196 newtons for 15 meters. But with this system to help us, with a mechanical advantage of 3, again, you could use a formula, but a lot of this just turns into common sense, to be totally honest with you. 15 meters times our mechanical advantage of 3 means we have to pull that rope for 45 meters for a grand total at a grand total of 65.4 newtons. So again, much longer distance we're pulling for, but at a much more reasonable force. Okay, cool, fantastic. Question number 4. Okay, we're going to look at some efficiency. Okay, so we've got a hand cranked machine that is designed to give a mechanical advantage of 10. To test open the machine, the worker cranks the handle with 15 newtons. So this 15 newtons, right, that is the input force. Okay, so if we are putting in 50 newtons, again, we're going output divided by our input. If we are putting in 50 newtons with a mechanical advantage of 10, then that means that we would expect an output to be 500 newtons, right? 10 times as much as what we were putting in. But in reality, this crusher only registers 475 newtons when we're still putting in the same 50 newtons, right? The same 50 newton input, which means our actual mechanical advantage of this machine is going to be, well, again, output divided by our input. It tells us the output, it's only 475 newtons. We're putting in 50, which means the actual mechanical advantage is only 9.5, okay? Which means that tells us that the efficiency of the machine is our AMA over our ideal mechanical advantage, 9.5 divided by 10, which means it's 95% efficient, right? We are losing 5% of this efficiency to friction, heat, anything else inside that machine. Now, to be totally honest with you, I was talking about a ratio of forces. You can look at the ratio of forces where the efficiency is just, we actually get out 475, we expect 500 newtons, that also equals 95%. They're exactly the same thing. You're not always given this force value, so you might need to do it this way, but both work. They're just ratios. It really doesn't matter. It's totally up to you. So that is a good overview of mechanical advantage. I'm going to stop this video here. There will be another one to follow up where we're going to look specifically at inclined planes. I know we've kind of already done it a little bit, but we're going to look specifically at that. It'll be a shorter video. So go ahead and watch that right now, and I'll see you in class.